Welcome back to Computer Lessons.
We have built a supercomputer capable of calculating the secrets of the universe and rendering photorealistic worlds. But right now, that machine is working in the dark. Without a way to visualize the billions of calculations happening every second, our computer is effectively useless to us. To bridge the gap between the silicon brain and the human eye, we need a translator. We need a window into the digital soul. Today, we are going to explore the technology of monitors. We stare at these glowing rectangles for hours every day, but few people understand the complex physics occurring right in front of their faces. At the most basic level, a screen is a mosaic made up of millions of tiny squares called pixels. But a pixel is not a single light. It is actually a trio of subpixels: red, green, and blue. By mixing these three colors at different intensities, we can trick the human eye into seeing over 16 million different colors. If you turn all three on at full power, you see white. If you turn them all off, you see black. But the engineering required to control this light is surprisingly difficult. For the last 2 decades, the dominant technology has been LCD, or liquid crystal display. An LCD panel is like a complex technological sandwich. At the very back, there is a strong light source called the backlight, usually a sheet of white LEDs pushing light towards your eyes. To create an image, we need to block some of that light selectively using liquid crystals. These microscopic crystals act like tiny shutters. When electricity hits them, they physically twist to block the light or let it pass through. However, these shutters are never perfect. Even when they are closed to show black, some of the strong backlight still leaks through the cracks. This is why, on a standard monitor, black looks more like a glowing dark gray. This fundamental flaw led to the development of different panel types: TN, IPS, and VA. TN panels are incredibly fast and cheap, but if you look at them from the side, the colors invert and look terrible. IPS panels are the gold standard for color accuracy and viewing angles, but they struggle with contrast. VA panels offer a middle ground with deeper blacks, but often suffer from slower motion handling. To solve the contrast problem, engineers invented Mini LED, which uses thousands of tiny lighting zones that can turn off individually. But recently, a new challenger has arrived to dethrone LCD entirely. Enter OLED, or Organic Light Emitting Diode. In an OLED screen, we remove the backlight entirely because the pixels themselves are the light source. If you want to show black, you simply turn the pixel off completely. This creates true black and infinite contrast, creating an image that feels almost 3D. However, OLED comes with a risk known as burn-in. Because the organic material degrades over time, static images like a health bar or news ticker can become permanently etched into the display. Now, let's talk about color science, a topic critical for artists. Most monitors use 8-bit color, giving us about 16.7 million possible colors. But professional monitors use 10-bit color, providing over 1 billion colors. This eliminates banding, those ugly stair-step lines you sometimes see in a picture of a blue sky, making gradients look perfectly smooth. This brings us to HDR, or High Dynamic Range. Real life is blindingly bright, but standard monitors are dim, usually hitting only 300 nits of brightness. A true HDR monitor can hit 1,000 nits, dazzling your eyes with realistic highlights while keeping the shadows pitch black. But be careful. Many cheap monitors claim to be HDR, but lack the hardware to actually display it. Always look for strict certifications like Display HDR 600. Now, let's discuss motion, specifically the difference between refresh rate and response time. Refresh rate, measured in hertz, is how many times per second the screen updates the image. A standard office monitor is 60 Hz, while modern gaming monitors run at 144 Hz or higher. The difference is transformative. Motion becomes fluid, and your mouse cursor feels like an extension of your hand. But high Hertz is useless without fast response time. This defines how fast a pixel can physically change colors from gray to gray. If the refresh rate is fast, but the pixels are slow to change, you get a visual artifact called ghosting, where a blurry trail follows moving objects. However, the monitor can only show what the graphics card sends it. If your GPU generates 200 frames but your monitor is 60 Hz, you are wasting those frames. Worse, if they are out of sync, you get screen tearing, where the image looks sliced in half. Technologies like NVIDIA G-Sync and AMD FreeSync solve this by forcing the monitor to act as a slave to the GPU. If the GPU drops to 45 frames per second, the monitor instantly slows its refresh rate to 45 Hz, keeping the image perfectly smooth. We must also consider resolution, which is simply the number of pixels. 1080p is the standard, 1440p is the sweet spot for gaming, and 4K provides incredible sharpness. But sharpness depends on size, a concept known as pixel density, or PPI. A 24-inch 1080p screen looks sharp because the pixels are packed tightly together. But stretch those same pixels over a 32-inch screen, and the image becomes blocky. This is why a massive 4K TV might look less sharp up close than a small smartphone screen. Ultimately, the monitor is the canvas of your digital life. It is the final link in the chain. You can have the fastest computer in the world, but if you view it through a cheap, washed-out screen with ghosting, the experience is ruined. We have now covered the output, but communication is a two-way street. We need to talk back to the machine. In the next video, we will explore input devices. We will learn how keyboards and mice turn your physical muscle movements into digital signals.
Tell me in the comments, do you prefer a high refresh rate for smooth gaming or high resolution like 4K for sharp visuals? Which one matters more to you? If you found this explanation helpful, please hit the like button and subscribe to Computer Lessons. Don't forget to click the bell icon so you don't miss our next class. Thanks for watching and keep learning.